Alright guys, this is Lesson 1 of AP Calc AB. Lesson 1 is an exploration of limits. Here, we'll learn about what limits are and how to work with them. So, what exactly is a limit? A limit is a value that a function approaches. A function can approach a value from just one side, either the left or the right. These are called one-sided limits. Let's start with a left-hand limit. Like, what is the limit of f of x as x approaches 3 from the left? To find this limit, we need to follow the path of the function coming from the left-hand side of 3. We would say that the limit of this function f of x as x approaches 3 from the left is 4. And what about the right-hand limit? What is the limit of f of x as x approaches 3 from the right? In this case, the right-hand limit is also 4, because the path of the function nears 4 as x goes to 3, coming from the right-hand side. Now, what about two-sided limits, or what I might call the limit overall? To find a two-sided limit, we need to consider both the left and the right-hand limits. If the left and right-hand limits are equal to each other, then the limit overall exists, and it shares the same value as the two one-sided limits. In our first diagram, we can see that the left-hand limit as x nears 3 is 4, just like the right-hand limit. Because these values are the same, we can say that the limit of f of x as x goes to 3 is 4. To make my point clear, this limit exists because the left and right-hand limits are equal to each other, and this limit goes to a particular value. And what happens in our next case, when the left-hand and right-hand limits have different values? Here, we see that the left-hand limit as x nears 3 is not the same as the right-hand limit. The left-hand limit is equal to 4, yet the right-hand limit is not. Instead, it goes to a value of 2. Since the left and right-hand limits are not equal to each other, we should say that the limit overall does not exist. We can use the acronym DNE whenever the limit fails to exist. Now that we know a bit more about limits, let's put this knowledge to the test. In question 1, we will find limits and function values from a graph. The first place we'll look at is when x equals -3 to answer parts A, B, C, and G. Dash in the line x equals -3 to see the left and right sides. Then, by following the path of the function from the left-hand side, we see the function going to this open circle, which represents a missing point or a hole in the graph. This limit appears to be 6, just like the right-hand limit. And because these limits are the same, we can say the limit overall is 6 too. But there does not appear to be a defined point at -3. This means that f of -3 does not exist, or is undefined. What about when x goes to 0? Let's view the left and right sides of this value. When we do, we see that the left side of the function takes us to this closed circle. This point is located at y equals 3, and the right side? The function takes us to the origin, where y equals 0. Consequently, the limit overall does not exist. Yet, the function is defined when x equals 0. We can see that f of 0 is 3, given to us by the closed circle on the y-axis. What about when x approaches -infinity? Where is the function headed as it goes all the way to the left in the xy plane? It appears that the function levels off, but is always approaching y equals 2. The limit here is 2, and that horizontal line could be considered a horizontal asymptote. The last place we'll look at in this graph is around x equals -2. Here, we see a vertical asymptote. And where does the function go on the left and right-hand sides of this asymptote? The path of the function goes up, all the way to infinity. This is true on both the left and the right-hand sides, so the limit exists. The limit of our function, as x goes to -2, is infinity. When would the value of a limit be equal to the value of a function? In other words, when would it be the case that the limit of f of x, as x approaches c, be equal to the actual function value at x equals c? Well, for the limit to equal a particular value, the limit must exist. This is a good starting place. Next, the function has to be defined at the very same value that the limit approaches. The defined point cannot be any higher or lower than where the path of the function is headed. Not only does the function need to be defined, it has to match, exactly, the limit value. So what does this mean? What we are actually doing here is showing that the limit shares the same value as the function, only at locations where the function is continuous. Through this investigation, we have given the definition of continuity. Here are 3 tenets that help describe continuity. It boils down to the fact that the limit of the function must be equal to the actual value of the function. A function can be everywhere continuous, like the function to our left, which is continuous over its entire domain of all real numbers. On the right, we see a function that is continuous over a closed interval from x equals a to x equals b. The intermediate value theorem states that a function f, continuous on the closed interval from x equals a to x equals b, will take on every value in between f of a and f of b at least once. Imagine that we didn't know what the function looked like over this interval. Instead, we only knew that the function had these endpoints at x equals a and x equals b, and the function was continuous. At the very least, these 2 points would have to connect. As we have drawn it, the lower endpoint is as low as f of a and the upper endpoint is as high as f of b. And there's this middle section in between. From this angle, it's clear that the function has to pass through this entire middle section of values, at least one time through. Yet, this does not mean that the function couldn't go outside of this section. It might. But if we only knew of the function's endpoints, and that the function is continuous, we can say without a doubt that the function will take on all values in between f of a and f of b. This is all thanks to the intermediate value theorem. We have, so far, talked a lot about continuity, but what about discontinuity? One type of discontinuity is what we see on the left, which is a removable discontinuity. This is where the limit exists, but the function value does not share this same value as the limit. It would be possible to make the function continuous by placing a single point in the path of the function. Without the function defined at this exact location, the function is not continuous. On the right, we see an example of a non-removable discontinuity. What we see, specifically, is a jump discontinuity, where the left and right-hand limits approach different values. But this is not the only type of non-removable discontinuity. Another example comes in the form of a vertical asymptote. When we look on either side of this asymptote, the function has to go up to positive infinity or down to negative infinity. In either case, there is no single point that could be placed in the graph to make the function continuous, like with what we see in removable discontinuities. Question 2 asks us to find the value of a to make the piecewise function f continuous. Here, we see that function f has 2 pieces, and these 2 pieces must connect to keep function f continuous. Specifically, the 2 pieces must share the same value when x equals 2. Solving this equation shows us that a would have to equal 7. Then, by graphing out the piecewise function, we can show that we have found the correct value of a. This is because we see a function that is perfectly continuous. See if you can answer part B on your own. Pause the video, and, when you are ready, see if you are able to get the same result. The correct answer is that b must equal 4. This is the only value of b that will make the piecewise function continuous. Graphing out function f, with b now equal to 4, can help prove to you that the function is continuous. The 2 pieces connect at x equals 4, and there are no discontinuities present in the graph. How can we evaluate limits without a graph? This all starts with direct substitution. When we need to evaluate limits, like in question 3, we should start by just plugging in the value that x is approaching. In part A, we see that x approaches 1. When we plug in 1 for x, we get a limit of 6. We can use direct substitution to answer every limit statement in question 3, including part D, which is a one-sided limit. Pause the video to see if you can follow the direct substitution method to find these limits on your own. Then, check your work to make sure that we are getting the same answers. If we are, then you are ready to move on to the next section. Now, what happens when we try to evaluate this limit, where x goes to 4? We get 1 divided by 0, which is undefined, and signals the presence of a vertical asymptote. Remember, that the function can only go up or down on either side of the asymptote, and it is our job to figure out which way the function goes on both the left and the right sides. With a chart of values leading to x equals 4, we can investigate the left and right-hand limits numerically to see if the two-sided limit exists. With these values of x that you now see in the chart, we see that the left-hand limit goes to infinity because the function values are getting more and more positive. The same is true for the right-hand limit. We now know that the limit goes to positive infinity. The graph of this function would show a vertical asymptote at x equals 4, with the path of the function headed upward on both sides of the asymptote. The limit exists because the left and right-hand sides go to the same place. This limit should be reported as going to infinity. Limits that go to infinity are called infinite limits. These limits increase or decrease without bound, and are often marked by the presence of a vertical asymptote. A graphical or numerical approach should be used to evaluate these types of limits. See if you can use one of these approaches to solve question 4, a one-sided limit. By using values that are less than 3, we can determine the behavior of the function on the left side. The function gets more and more negative, indicating that the function goes to negative infinity, even though the function is undefined. The graph of this function shows a vertical asymptote at x equals 3, with the path of the function headed downward on the left-hand side. This one-sided limit goes to negative infinity, regardless of what happens on the right. Direct substitution can sometimes lead to indeterminate forms, or expressions without a clear value. The most important indeterminate forms are 0 over 0 and infinity over infinity. We will have to do more than a simple direct substitution to find limits in an indeterminate form. For example, part A of question 5 first yields 0 over 0, but factoring will reveal the actual limit. We should, first, factor and simplify the expression. Then, we can retry direct substitution. Doing so reveals a value of 2. Go ahead and try part B, which also involves factoring. Part C is a little different. It requires expansion to simplify the expression. See if you can expand and simplify the expression to get the correct answer. The limit should be 2x. Now, part D can be answered through factoring or through multiplying by the conjugate. Try to follow both strategies. Both are common ways to approach limits that have a binomial expression with square roots in them. As you will see, the factoring method ultimately reveals that the limit is 1 over 2 root 2. We can get this same result by using our other method, which is using the conjugate to create an equivalent fraction. Using the conjugate might be a new technique for many of you. The conjugate of the binomial uses the opposite sign in between the two terms. Addition would go to subtraction. Subtraction would go to addition. But through some expansion and simplification, we can determine the limit. Again, the limit is 1 over 2 root 2. We just used a different method to get there. One way to answer the last limit in question 5, which shows an indeterminate form of infinity over infinity, is to divide the numerator and denominator by x squared. Note that any number divided by infinity goes to 0, and many terms in our limit expression will zero out as a result. With all these fractions going to 0, we are left with 5 over 2, which is the answer to this problem. Limits like the ones we saw in question 5 can be solved using L'Hopital's rule. This is an advanced technique that requires using derivatives, a skill that will be addressed more thoroughly in our next lesson. For now, we will introduce the basics behind derivatives. The derivative of a function tells us about the slope of the function at any point. One way to find a derivative is through power rule, which works whenever x is raised to some power. We bring down the power as a coefficient, then lower the new power by 1. For example, if x is raised to the 5th power, then the derivative is 5 times x to the 4th. Here's another example. Each term represents a function that has its own derivative, or slope. The slope of x squared is 2x, by using the power rule. The last two terms can be thought of as a line in mx plus b form, where the slope of the line is 3. The derivative, here, is 2x plus 3. One other derivative rule we need to know in this section is that the derivative of sine of x is cosine of x. Knowing this, We can now tackle question 6. L'Hopital's rule allows us to evaluate limits in the indeterminate form 0 over 0, or infinity over infinity. We can take derivatives of the numerator and denominator independently to get into a place where direct substitution reveals the value of the limit. Part A, evaluated through L'Hopital's rule, shows that the limit is 2. Now, pause the video and try out the rest of question 6 by using this new method. Here are the solutions to the rest of question 6. Did we get the same answers? If so, you have successfully used L'Hopital's rule. Now what about limits at infinity? These limits occur when x goes to positive or negative infinity. The limits might increase or decrease without bound, they might approach some number, or they might not exist at all. Here are some examples that you can write down. We have an unbounded function on the left, a bounded function on the right, and a periodic function whose limit at infinity does not exist, below. This last case has a limit at infinity that does not exist because the function continuously goes up and down, never approaching a single value, and never headed in one direction. Many limits at infinity can be evaluated by using growth rates. You should know that a number over infinity goes to 0, and infinity over a number goes to infinity. We can use this to our advantage to evaluate the given limits. In our first example, let's view ln of x as one function and x as another. In the xy plane, it becomes clear that x outgrows ln of x over time. The slower growth function can be thought of as going to a number compared to our faster growth function that heads to infinity. In our second case, we have a similar dynamic. The function e to the x power outpaces, or outgrows, the function x. As a result, we end up with a limit that goes to infinity. Let's summarize some important rules when it comes to growth rates. In general, exponentials grow faster than polynomials, which grow faster than logarithms. For exponentials, a larger base indicates a faster growth rate. For polynomials, and even radicals, a larger exponent indicates a faster growth rate. Lastly, note that factorials grow faster than exponentials. We can use growth rates to help us answer all parts of question 7. Pause the video, and let's see if you can correctly find each limit based solely on growth rates. Here are the solutions. Did you identify the highest growth terms to correctly find each limit? If so, you correctly applied your knowledge of growth rates. But what about L'Hopital's rule? These limits can also be evaluated this way, so long as you know how to take derivatives. You should be able to answer parts A and E with L'Hopital's rule based on today's discussion. Here is a special case. These limits cannot be determined by growth rates because the highest power on x is the same in the numerator and denominator of each limit. A shortcut is to use the ratio of leading coefficients, or you can also use L'Hopital's rule, which is especially helpful for parts A and B. Part C is a little tricky. We can focus on the highest growth terms, but we need to be careful to notice that the denominator will stay positive, even as x goes to negative infinity. Do you see why? Well, x is being squared, and also, the output of a square root is always positive in the real number system. The limit in part C should be reported as -3 over 2. Here's a challenge problem. How do you suppose we find this limit, which first shows the indeterminate form of infinity raised to the 0 power? Well, we can introduce logs to bring down the exponent. Then, with growth rate analysis, or even L'Hopital's rule, we can continue to find this limit. By the end of our solving process, we should find that the original limit statement, the limit of x raised to the 1 over x power, as x goes to infinity, is 1. We can also use the squeeze theorem to evaluate some limits, especially ones that involve periodic functions like sine and cosine. Growth rate analysis would tell us this limit goes to 0, but squeeze theorem gives us a more formal route to this answer. We can start by saying that sine must be in between -1 and +1. Then, we divide all parts of the inequality statement by x and take the limit as x goes to infinity. What do we see here? We see that the limit gets squeezed to 0. This is an appropriate use case for squeeze theorem and one that you should be aware of in the AP Calc curriculum. Earlier, we talked about how a function's derivative gives the slope at a single point. This is called an instantaneous rate of change. But how can limits help us define a derivative? Well, it starts with finding the slope between just 2 points. Remember, that slope reflects a change in y divided by a change in x. This is a good starting place for us. Let's now define 2 new points a different way. One point is x and f of x, and the other point is x plus h and f of x plus h. What happens when h goes to 0? It brings us closer and closer to the 2 points meeting in just one place. A slope calculation, in conjunction with a limit statement, brings us to the definition of a derivative, where the derivative of f is called f prime. This is a key testing point in the AP Calc exam, so make sure to memorize this definition of a derivative before moving forward. Another definition is useful to find the derivative at a particular value of x. Let's find the slope between these 2 points, then take the limit as x goes to a. This limit statement would give us the derivative of f when x is a. This is a slope at a particular value of x, not a general rule for the derivative function. Still, it is fair game on the AP exam in May. You might also see definition 1 used with a value of x already plugged in, like when x equals a. This would also amount to f prime of a, or the derivative of f when x equals a. As we move forward, we will use definition 1 to find derivative functions. In question 10, let's use this definition to find f prime of x. Then let's evaluate the derivative at a particular x value. In part A, we will need to expand out f of x plus h and use this expression into definition 1. After simplifying and evaluating the limit as h goes to 0, we should find that f prime of x is equal to 2x. This means that f prime of 3 is 2 times 3, or 6. We have used the limit definition to find the derivative, but do you remember the power rule shortcut? We could get the derivative function more easily just by using power rule. We bring down the power and lower the new power by 1. Just like that, we find that f prime of x is 2 times x. Now do your best in parts B and C to find derivatives with the limit definition, as well as the power rule shortcut. Pause the video and see if we are getting the same results. If we are, then you have correctly used both methods to find derivative functions and to evaluate them at particular x values. You should see that the limit definition involves a lot of algebraic manipulation, and it ends up being a lot easier to just use a derivative shortcut. And that's just the thing about calc. The class often teaches you the hard way before the easy way. My goal here is to introduce you to the easy way as soon as possible to make the class more manageable for you. But do your best with these problems. Part B should show a derivative function that is equal to negative 1 over x squared, making f prime of negative 1/2 equal to negative 4. To use power rule here, write the function as x to the negative 1 power. Then you can drop down the power and lower the new power by 1. The result is exactly the same as before. Using the limit definition and using the power rule are both correct ways of finding a derivative. Part C should show a derivative of 1 over 2 root x. But how do we get here? To do this by using the limit definition, you will need to multiply by the conjugate, a technique we mentioned earlier. Here is what that looks like. Did you get the same answer? And what if we use power rule instead? To get this derivative using power rule, we will need to rewrite the radical as an exponent. The power would be 1/2, and we can use power rule, just like before. The answer is the same as with using the limit definition, but it was much easier to get here thanks to this shortcut. Question 11 will be our last problem. Do you see anything interesting about these limit statements? They are in the format of the limit definition of a derivative. In part A, we see that f of x is equal to x cubed. Its derivative is 3x squared. By using power rule, we can evaluate this limit, because both are valid ways of finding a derivative. Now what about part B? This is a little different. We see a value of x already plugged into the limit definition. Still, we can see that f of x would be cosine of x. But what is the derivative of cosine of x? It is actually negative sine of x. This is a new derivative rule that you will be responsible for knowing. Now we can evaluate the derivative at the value of x from our original limit statement. The derivative at pi over 4 is equal to negative root 2 over 2. And that completes this question. It also completes our exploration of limits. See you again in our next lesson.